All right, happy whatever day it is. We're going to try this one again. Realize the sound it did not take on the previous video, so here goes. This next topic that we're going to look at is continuing on this notion of the derivative. We've just spent some time finding the derivative at a fixed number, some single point. Now we had two definitions. We had the first one where we were taking two distinct points, like x approaching a. That's like taking 2 points on a graph, a secant line, and taking them infinitely close together. The second definition for our derivative, we were using that h approaches 0 notation. And the h is the distance away from our value. So it's taking the distance away from some number and pulling that back towards our desired point to find the slope of the tangent line. The whole idea is that the derivative of a function is the instantaneous rate of change of a function. It's the rate of change at a single point. It is the instantaneous rate of change it's the slope of a single point on a curve. It is the slope of the tangent line to a curve at a single point. So that's the whole notion behind the derivative. The derivative gets us the slope at a single point on a curve. Now, instead of some value for a, we're going to put this in terms of our function notation. Rather than trying to say a is 5 or a is 2 or whatever, we're going to say for any value, I'm going to replace a with some variable x. So the notion here is we're moving back to our function notation. Rather than the derivative at some indicated value, we are the derivative at any value of our curve along the way. Really is the same thing. We are just substituting back for x rather than a or a designated value. And what we have there is we've got this brand new function. This function we call the derivative of f, the derivative as a function when that limit is defined. Now, geometrically, once again, we've seen this a little bit. The value of f prime at x, the derivative of f at x, that f prime of x, is the slope of the tangent line to the graph of f at that specific point, x, f of x. That's our x, y coordinate somewhere on our curve. And we're going to be using this and comparing the graph of a function compared to the graph of the derivative of that function. The whole idea is that the derivative is the slope. Our first example is we're going to take some function, some graph here, doesn't matter what the equation is for that, and I want to use this and sketch the graph of the derivative. Now, there's a few key points that I recognize, and I'm going to be graphing this right on top here. The derivative is the slope of the tangent line. I'm going to look, starting off, these three specific values. Those are the turning points of our graph. At that point, our graph starts going down and it switches to going up. That peak, our maximum, we go from positive to negative. We're switching directions. And that valley, our graph is going down, it is decreasing, and then it changes to being increasing as we move left to right. Now, the slope of the tangent line at those 3 points is going to be 0. Because we have a horizontal tangent line at those points. So we use that as the first kind of guideline towards graphing the derivative function, f prime of x. Wherever we have a peak or a valley, the horizontal tangent, our slope is going to be 0. So the graph of our derivative function is going to be 0 at those points. Next, I'm going to look at in between. I don't want to delete those. I'm going to be looking in between. All the way to the left, our graph starts off around here about y equals 2. And from that point onwards, our graph is decreasing. It has a negative slope. If we look at the tangent line, it has a negative slope. But as we draw closer to that valley, we have less of a negative slope until we eventually reach a 0 slope. So what's happening is we have a steep negative slope and we are approaching a 0 slope. And so our derivative is going to be negative over that space. Below the x-axis, that means the derivative, the slope, is going to be negative. in between those two zeros, from that horizontal tangent to the next horizontal tangent, our graph is increasing. We've got a positive slope at any point along the way there. Now our tangent line starts off with a slight positive slope. It has an increasing positive slope, and then the slope decreases, still positive, until we get back to that horizontal tangent. So what's happening is there, right around that point, is going to be the greatest positive slope, maybe about 1. Go up, and our slope is decreasing, but still positive on that interval. Now between the next pair of horizontal tangents, we have a slight negative slope, very steep negative slope, and then we go back to having a slight negative slope until we reach our 0. Now I'm looking at right around that halfway point, we're going to have the greatest negative slope there, maybe about -2, just to estimate. So I'm going to be down around that point. Slight negative, greater negative. The negative reaches, the maximum decreasing rate, and then it increases, still negative, back to that 0. That's what I want. So we've got a 0 horizontal slope, slight negative, steeper negative, but then it's going to be less negative until we get back to the 0. Now the rest of the graph, slight positive, greater positive, and even greater positive. It's going to become a positive curve, or its derivative is going to be positive from there on out, because we keep on increasing the rate, increasing the slope. And our derivative starts off slight, and then it starts increasing. So we have something that could be the graph of our derivative of x. It's all about the slope. Let's go on and find some functions. We're first going to start off, find some derivatives. I'm going to do this using both of our definitions here. Now, we're given a function, x cubed minus x. I'm going to find a formula for the derivative of that function. We have two different methods that we've used so far. We have the x approaches a limit, or we have the h approaches 0 limit. Now, I've got these set up already. I'm going to keep on expanding these and then simplifying to take that limit as x approaches a. For the top, we've got that placed in there. We've got f of x subtract f of a. I'm going to open those parentheses. So now we have the limit as x approaches a. That will be x cubed. And I'm going to group as x cubed subtract a cubed. And we're going to have subtract x, add a, all over x subtract a. And remember, that negative distributes, which is why that is adding a. Now, the whole notion of this is I need that x subtract a factor to be eliminated so that we can take our limit. I'm going to use some factoring here. I'm going to factor by grouping. I'm going to take the x cubed minus a cubed, and I'm going to take that negative x adding a and factor out of that. That will yield limit as x approaches a. It's going to be x subtract a. It's x squared plus ax plus a squared minus 1 multiplied by x minus a. Let me factor that. And what I see is, there's an x minus a factor, an x minus a factor, and an x minus a factor. Everything has that common factor, so I can cancel that. Now, when we apply the limit, x approaches a, this is going to become a squared plus a squared plus a squared minus 1, giving us f prime of a is equal to 3a squared minus 1. But rather than being some arbitrary a, I want this as a function. So this is going to be f prime of x is equal to 3x squared minus 1. That is our derivative function for f of x, remember, x cubed minus x. Seeing that done out now, that is one limit definition. Useful if we're factoring and we're looking for that x minus a factor. If instead we're using our h approaches 0 notation, I'm going to expand the parentheses. I'm going to multiply that out. This will give us the limits. H approaches 0. That will be x cubed plus 3x squared h plus 3x h squared plus h cubed plus h, subtract x cubed, add x, all over, oh, no mistake there, that should be subtract there. That's not going to work out, so that's going to be subtract, all over h. The difference here is that we don't have to factor per se, but we've got to be able to distribute our parentheses. Just neaten that. Subtract x minus h once we open that parentheses. So now neatening up, we've got limit h approaches 0. Notice h cubed, subtract h cubed. Add x, subtract x. Grouping what we have, 3x squared h plus 3x h squared plus h cubed minus h divided by h. And since now everything has an h factor, I'm going to cancel that h, giving us limit h approaches 0. That will be 3x squared plus 3xh plus h squared minus 1. And now applying our limit as h approaches 0, 3xh goes to 0, h squared goes to 0, and we have f prime of x is 3x squared subtract 1. We better get the same thing, but it's the approach. Do I need to factor or do I need to open my parentheses and multiply? What we have is a function for our derivative. Now let's go back and compare the graphs of those two. We had the blue was x cubed minus x. That was our original function. Now I factored this to make it a little bit easier to graph. At the same time, we have our derivative function, 3x squared minus 1. Graphing that, I recognize as a y-intercept of -1. We're going to have solution zeros about plus or minus, that's 1 over root 3. Now looking here, our graph, positive slope until we reach that horizontal asymptote. So our derivative is positive until we reach that 0 that corresponds to that horizontal asymptote. Then we have a negative slope until we reach kind of a maximum decrease, coming back to a less negative slope. So negative slope, back up until we hit 0. And that 0 corresponds to that minimum point where we've got a horizontal tangent, and then from that horizontal tangent onwards, back to have a positive slope, and it's an increasing slope. So the graph of our derivative is increasing. Isn't that nice? Let's try another function, and we're going to talk about the domain, and I'll bring up the graph once again. So our next function is the square root of x. We've seen this a few times. But finding a formula, finding the derivative of f, we know right at the start that the domain of the square root is everything 0 and greater. So from 0 to infinity, including 0. Let's go on and find that derivative. I'm going to use the x approaches a approach. Now, to do this, I'm going to multiply by our conjugate, so square root of x add square root of a, over square root of x add square root of a. That is the difference of two squares when we multiply that, yielding us limit x approaches a. That will be x minus a, already handed to us, over x minus a, multiplied by root x add root a. Right away, you can see that common factor is eliminated. Result, limit x approaches a, 1 over root x plus root a. And when I apply that limit, that's going to give us f prime of a equals 1 over 2 root x to root a, which, substituting back for our function f of x, 1 over 2 root x. Okay, now the domain of that, the domain of f prime of x, we still have that square root, but we can no longer be equal to 0. We no longer include 0 because then we would be dividing by 0. Now let's think about that in context of a graph. We have y equals the square root of x. Look at that tangent line right at the start. That's a vertical tangent line. Now if we graph simultaneously y equals 1 over 2 root x, we have a rational statement, not a rational function. We're going to have a graph that looks like that. Our tangent line at the start is vertical. Okay, which makes sense why we have, as we're approaching 0 from the left, an infinite slope. Vertical tangent line, our slope is undefined, is infinite. Well, our slope is always positive, but it's just less and less positive. Always positive, but less and less positive as x is increasing. Let's carry on. Another example, we now have a rational function. So our function is 1 minus x over 2 plus x. Keep in mind that our domain is negative infinity to negative 2, negative 2 to infinity. I'm going to go ahead and find our limit function. I'm going to do so by getting a common denominator. So make certain that it's clear to you how I'm doing that. 1 to subtract x, I'm multiplying by 2 plus a. I'm subtracting, I have 1 minus a, and I'm multiplying by 2 adding to x. All over, that will be 2 plus x. Get rid of that extra x. 2 adding to x, multiplied by 2 plus a. And we still have that. I'm going to write it as 1 over x minus a. Dividing, I've got that statement. I'm going to open those parentheses and multiply and simplify some statements. Limit x approaches a. It will be 2 adding a, subtracting 2x, subtracting ax. And I'm subtracting, I've got 2 plus x minus 2a minus ax, all over 2, again, 2 plus x, 2 plus a, that's 1 over x minus a. I'm going to distribute that negative. Limits x approaches a, 2 plus a minus 2x minus ax minus 2 minus x, add 2a, add ax, 2 plus x, 2 plus a, 1 over x minus a. Newton, we've got 2 minus 2. We have minus ax plus ax. I think that does that. Limit x approaches a. Now we have a, 2a, so we have a total of 3a. Subtract 2x, subtract x. That is minus 3x. 2 plus x, 2 plus a times 1 over x minus a. In that numerator, I'm going to factor negative 3. Limit as x approaches a. Factor negative 3. I'll leave us with x minus a. There's our common factor. 2 plus x, 2 plus a, x minus a. And applying our limit definition, f prime of a would be negative 3 divided by 2 plus a squared, or f prime of x is negative 3 over 2 plus x quantity squared. Notice our domain still does not include negative 2, which makes sense because if negative 2 is not in the domain of the function, you're not going to be able to find the slope at negative 2. So the domain of the derivative is always going to be what we started off with, but then the open set inside of a closed set, if we in fact start off with a closed set. Now, another talk about notation. Different notations that we'll be using. I've been using this f prime of x. There are times when we are talking about geometry, and I've got a curve in terms of y. I might list this y prime of x. I've mentioned before dy dx. Well, d coming from delta y over delta x, meaning the change in y over the change in x, thinking slope, that just derives, pun intended, from the Greek letter delta for change. So dy dx is an equivalent statement, meaning the change in y over the change in x. We can write that as df dx, meaning the change in f, back to our function label, with respect to the change in x. Or we can treat this as saying d dx. That is the derivative with respect to the rate of change of x. So the derivative in terms of x of a particular function. Another notation for evaluation, we have seen f prime of a, indicating that we are substituting an a. If we use this dy dx notation, we'll use this vertical line, and I'll write x equals a specific value. That's indicating that we are going to plug in a value into our derivative. Now, onto this notion of domain. Let's define something being differentiable. A function is going to be differentiable at a if, well, the derivative exists. Now, when does that exist? Let's go back to our limits, all coming back from the limits. When does a limit exist? Well, a limit exists when the left-hand limit matches the right-hand limit. A function is differentiable on an open interval. We no longer require a closed interval, but a function is differentiable on an open interval, so a, b, or if we have one or both of our endpoints being infinity, if it is differentiable at every single value in that interval. We no longer require a closed interval, not the endpoints. Now, let's think about this. A function is differentiable at a if that derivative at that value exists. And that comes from the limit, meaning the left-hand limit matches the right-hand limit. When is the absolute value of x differentiable? Well, thinking derivative is slope. Absolute value are two linear statements. We have a slope, -1, for all values less than 0. We have a slope, +1, for all values greater than 0. Well, look at what happens. What about right at 0? If we were to take the limit as x approaches 0 of f of x minus, start that again, limit as x approaches 0, take the absolute value of x, subtract the absolute value of 0 all over x. Well, at 0, we're going from a slope of -1 to a slope of +1. Right at 0, it's not defined. And if we were to think about the graph of that derivative, we would end up with something like that, or exactly this. This is the derivative of, I'm going to write that d dx of the absolute value of x, meaning the derivative of the absolute value of x. At 0, notice we have a jump discontinuity in the derivative. There is no derivative, no limit as x approaches 0. So the limit as x approaches 0 of f prime of x does not exist. No derivative. Now, where else is a derivative not defined or does not exist? Where else does a function fail to be differentiable? We've got a few different examples. Now, first off, we're going to use this new theorem. If a function is differentiable at a value a, it is guaranteed to be continuous. So differentiability implies continuity. If something is differentiable, it must be continuous. It doesn't go backwards. Just because something's continuous does not mean that it's differentiable. Absolute value is continuous, but is not differentiable at 0. So when do we not have a derivative, or when are we not differentiable? First off, so when we have a corner or a cusp. That's that point where we're changing slope immediately. Notice we have a positive slope, and then we immediately switch to a negative slope. So at that point, f prime of x does not exist at a corner or a cusp. From here, back to the stop theorem, if a function is differentiable, then it is continuous. If we take the contrapositive, meaning we negate the second term, we negate the initial term, and we swap, it's also a true statement. If f is not continuous, then it is not differentiable. So we are not differentiable if we are not continuous. So anywhere where we have a discontinuity, our derivative is not defined. And a third place where we will not have a derivative, or our derivative is not defined, is when we have a vertical tangent line. Well, what's happening there, our vertical tangent line, our limit, thinking either as h approaches 0 or the limit as x approaches a, is going off to positive or negative infinity. That slope is going to be positive or negative infinity. That's not a value. So our function is not differentiable when there's a vertical tangent line. Now, I like to think about differentiability. It's all about the smoothness of a graph, or a function being locally linear. Here's an example where we have a tangent line. And the idea is it's smooth at that point. If we are to zoom in, and you can see the crossaways or the cutaways there, zooming in, our function looks like a straight line. And if we were to zoom in enough, thinking on the calculator or Desmos or some other activity, it would look just like a straight line passing through a point. So our tangent line is almost identical over that small scale. It's smooth. Compare that to a corner or a cusp. We're not differentiable because no matter how much we zoom in, we're going from one tangent line that's got one slope to an immediately changed slope on the opposite side of that point. It's sharp. Ouch. You don't want to touch that because you're going to prick your finger. Not differentiable. Now, the last thing we've got today is higher derivatives. We can take the derivative of a function. What if we take the derivative of a derivative function? Let I'm going to go back and use physics as an analogy. In physics, we can start off talking about like a position function. A function describing your position or your displacement, your current location. Well, the rate of change of displacement, namely s prime of t, the rate of change of your position with respect to time, displacement versus time, that's our velocity. So velocity is the derivative of our position. It's the rate of change of our position. We can also take the next step, the rate of change of velocity. So v prime of t. V prime of t, well, that's the acceleration. Acceleration is the rate of change of velocity. Or, putting that together, acceleration is then the rate of change of position. So it's kind of a second rate of change. It is the derivative of the derivative. We call that the second derivative. And we're going to denote that with 2 tick marks there. So s prime prime. Now, I like to view this kind of as a hierarchy. And I think about taking the derivative as you're moving down this hierarchy from position to velocity to acceleration. So velocity is the rate of change of position, top right, and acceleration is the rate of change or derivative of velocity, which is also the second derivative of position. So we're moving down from position to velocity to acceleration. And then we can repeat that process, the third derivative, the fourth derivative. If we're talking physics, where we go from position to velocity to acceleration, a prime of t, the rate of change of acceleration, which would be the third derivative, notice 3 tick marks of position, we call that the jerk. And if you think about like you're driving and you just have choppy acceleration, that's the jerk. It's the sudden rate of change of your acceleration. So this process can go on as long as a derivative is defined. Now let's go on and find a second derivative. I'm going to use the example from number 2 when we started off with x cubed minus x. We found earlier that the first derivative is 3x squared minus 2. That was in example 2. The second derivative, we're just going to apply our limit definition an additional time. So here, f double prime or f prime prime of a is going to be the limit as x approaches a, or we could do h approaches 0. And instead of just f of x, I have f prime of x minus f prime of a. I can use my same limit process. So I'm going to expand, distribute that, and group. I've got x approaches a. It'll be 3x squared. Subtract 3a squared. Subtract 1, add 1 over x subtract a. Notice that subtract 1, add 1 cancels. We can factor that 3. We have limit. So x approaches a. That's 3. That would be x squared minus a squared, or x minus a. Ooh, x plus a. I really hope volume took this time. X minus a. There's our common factor. And when we apply our limit, we end up with 3 multiplied by 2a. So f prime of a equals 3 times 2a, or 6a. Therefore, the second derivative of our function is 6x. Let's go on, find some more. We've got our function. We found our first derivative earlier. We just found the second derivative. Let's go find the third and the fourth. Now, the third derivative, notice I'm using 3 tick marks. I call f prime 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 or f triple prime or the third derivative. Beyond that notation, we would use a superscript in parentheses for the specific higher order derivative that we're taking, be it the fourth derivative, the fifth derivative, etc. We just found the second derivative. Finding the third derivative, I can repeat that limiting process. Limit x approaches a. I'm going to factor that 6, x minus a. This is becoming easier and easier. X minus a. And we've got 6. So f prime prime prime. The third derivative function is 6. And one more. So the fourth derivative, that is going to be the limit x approaches a. That will be 6, the third derivative, subtract 6, f prime 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 of a, all over x minus a. That's 0. So the fourth derivative of our function is 0. But we already knew that. We didn't need to go through that. Let's think about how we already knew that. If I look at a graph, well, f prime 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 is 6. That's a horizontal line. The slope of a horizontal line is 0. And actually, in this case, if we go back to our second derivative, we had 6x. 6x, that's a linear equation. So f prime prime is equal to 6x. We know the slope of that. That slope was 6. Oh, it was there all the way along. Not so obvious going from the first derivative to the second derivative, y is 6x. Not so obvious going from our parent function to 3x squared. But I'm also going to point out here that we went from a cubic polynomial to a quadratic polynomial to a linear polynomial to a constant. It went right down in order. It's kind of convenient. So here we've got derivatives. Try it out. We're going to play around. Thanks for listening. See you later.